This is a production of the Chemical Education Material Study.
Chemists divide the substances around us into compounds and elements. Let's look at the elements. Here is the chemical element potassium. It cuts easily, and its shiny surface dulls as it reacts with air. Potassium also reacts with water. By contrast, the element phosphorus is stored under water, but it too reacts rapidly with air. Phosphorus and potassium are similar in reacting with air, but they differ in appearance and in their behavior toward water.
Here are most of the some 100 known elements. They have similarities and differences in appearance. What can we do to order and organize the elements as in the periodic table, and perhaps even to learn and understand some of their properties?
Well, we can make observations and look for similarities and regularities. You can see similarities among these elements. Most are solid. Some are gaseous. Many of the solids are shiny. A few are not. Shininess indicates that the element is a metal. Many metals, such as silver, are ductile. That is, they can be bent without breaking and, like potassium, be cut smoothly. For contrast, sulfur lacks the shine we associate with metals, nor is sulfur ductile. Such elements are called nonmetals. Let's sort the metals from the nonmetals, first using shininess as a criterion. Here are metallic copper, chromium, zinc, samarium.
In addition to being shiny, metals are good conductors of heat and electricity. When we touch these probes together, the meter shows high electrical conductivity. When touched to silver, we see that silver is also a good conductor. Let's check potassium. It is ductile and shiny. It is also a good conductor. Silver and potassium are metals. Phosphorus looks non-metallic. It caught fire in air, and so must be tested under water. Water does not conduct. Neither does the phosphorus. Sulfur looks non-metallic and does not conduct. Sulfur and phosphorus are non-metals. Lithium is somewhat ductile and looks metallic. Like potassium, its clean surface reacts with air. The lithium turns black, except where covered with oil. The shininess and ductility of lithium indicate that it is a metal, so we expect it to conduct. It does. We proceed with the task of sorting elements into metals and nonmetals. Some conduct, and some do not. Here is carbon in the form called graphite. It has little shine, and under stress it breaks rather than bends. Graphitic carbon is hardly metallic in these properties. But look, it is an excellent conductor. It conducts like a metal, but is not very shiny or ductile.
When we use the criteria of shininess, ductility, and electroconductivity, we find that there are about 4 times as many metals as nonmetals. Evidence is inconclusive about carbon and silicon. We identified 16 elements as non-metallic. We sort out the elements, which are gases, at room temperature. The atomic numbers shown in red indicate the number of electrons held by the individual neutral atoms. Here are the gases. Let's sort out the non-metallic solids. Bromine is liquid at room temperature. We have subdivided the nonmetals into gases, liquids, and solids. Can these gases be further classified on the basis of their chemical reactions?
Potassium, we observed earlier, reacted with air. Since air contains several gaseous elements, let's see which of the gaseous elements will react with potassium. This system of glass bulbs and stopcocks allows control of the flow of the gases we wish to test. Each of the top bulbs has been filled with one of the gaseous elements: argon, chlorine, fluorine, helium, hydrogen, krypton, neon, nitrogen, oxygen, and xenon. When this stopcock is opened, the gas can leave the bulb. A small piece of potassium metal has been placed in each evacuated reaction tube. Each piece of potassium is coated with oxide, the result of reaction with air. Let's try argon first. Opening the stopcock allows the argon to enter the reaction tube containing the potassium. There is no apparent reaction. Let's try heating. The potassium melts. The oxide coat cracks, exposing shiny potassium, which slowly vaporizes, carrying the oxide dust with it. The quiet, shiny surface indicates that no reaction occurs between the gaseous argon and potassium. Next, chlorine and potassium. There is no apparent reaction, perhaps again due to the coat of oxide. When heating exposes fresh metal, reaction does begin. Solid potassium chloride forms. Next, fluorine enters a reaction tube. Again, after slight heating, reaction occurs. When surrounded by gaseous helium, the potassium melts quietly. Oxide dust escapes, but there is no evidence of reaction. Apparently, helium is inert toward potassium. With hydrogen gas, gradually reaction occurs and considerable product collects on the sides of the tube. Analysis would show potassium hydride. Krypton is next. There is no evidence of reaction with molten potassium. Neon is now tested. Again, oxide dust escapes, but neon does not react with the metal. Our next gas is nitrogen. Nitrogen does not react. How about oxygen? It didn't take much heating to start that reaction. Oxygen is certainly reactive with potassium. And now the last one, xenon. Xenon is inert with potassium. Comparing all the tubes, we find 4 of the gases gave white, solid products with potassium. Apparently, the other 6 gases are inert toward molten potassium.
You may remember something in air reacted with freshly cut lithium. Let's try the previously inert gases with lithium. Nitrogen was inert toward potassium. Look at the darkening area. Nitrogen does react with lithium. Nitrogen is not inert. Here are argon and lithium. The lithium melts, but argon does not react. Argon, helium, krypton, neon, and xenon give identical non-reactive results with lithium. We might tentatively classify these 5 apparently inert gases as a family of chemical elements. For almost 100 years, they were called the inert gases. You saw phosphorus react vigorously with air. Let's try phosphorus with these 5 apparently inert gaseous elements. Pieces of phosphorus have been placed in the tubes, and we're ready to try the reactions. Highly reactive fluorine first, just for comparison. As soon as it strikes the solid phosphorus, reaction begins. We now let the inert gases, unreactive so far, into the 5 reaction tubes containing the phosphorus. The phosphorus is heated until it actually boils. The solid you see on the walls is not from a chemical reaction. It is condensing phosphorus. Again, the 5 gases are unreactive. Let's group these gases together as a family of elements, the noble gases, all with similar chemical properties. Experiments show that the atomic numbers of these noble gases are 54, 36, 18, 10, and 2. This is the number of electrons surrounding the nucleus of each unreactive atom. Now, highly reactive fluorine has 1 less electron per atom than the gas neon. Are there chemical similarities among fluorine and the other elements with 1 less electron per atom than the noble gas family? Are hydrogen, fluorine, chlorine, bromine, and iodine a family?
We saw phosphorus react vigorously with fluorine. Will these other nonmetals do the same? Pieces of phosphorus have now been placed in the reaction tubes and all the gas pumped out. We add gaseous hydrogen. Upon heating, the phosphorus boils and condenses, but there is no reaction. When we add chlorine to phosphorus, there is a reaction. Bromine also reacts, as does iodine. The phosphorus reacted with all of this possible family except the hydrogen. You saw earlier that hydrogen, fluorine, and chlorine did react with potassium. Do bromine and iodine react with potassium? First, we try bromine gas. Once the heating breaks the crust on the potassium, reaction starts. Solid potassium bromide forms. Since both iodine and potassium are solid, we have placed the potassium in the inner tube and iodine in the outer tube. Heating gives gaseous iodine. In a few moments, iodine enters the inner tube and reacts with the potassium, producing solid potassium iodide. We remove some of the potassium iodide and the other 4 products and check their reactivity with water. The chlorine compound dissolves quietly. So does the fluorine compound. The bromine compound acts similarly, as does the iodine. When water is placed on the hydrogen compound, it gives a rapid evolution of gas. Again, all but the hydrogen compound are similar. Thus, hydrogen is not usually included in this family of reactive and chemically similar nonmetals, each with one less electron than a noble gas. This family of elements, called the halogens, consists of fluorine, atomic number 9, chlorine, atomic number 17, bromine, atomic number 35, and iodine, atomic number 53.
You have now observed a good many reactions with potassium, which has one more electron per atom than argon. Since the elements with one electron per atom less than a noble gas seem to be a family, you might suspect elements with one electron per atom more than a noble gas would also be a family. These elements are lithium, sodium, potassium, rubidium, and cesium. Potassium reacted with chlorine. Do the other members of this possible family also react? The gas bulbs are now filled with the chlorine, and pieces of the 5 metals are in the reaction tubes. Here are chlorine and lithium. When the lithium melts, there is a reaction with the chlorine, producing solid lithium chloride. Sodium melts. The crust cracks. And the liquid sodium reacts vigorously, producing solid sodium chloride. Here are potassium and chlorine. Again, the reaction product collects on the walls of the tube. Next, we try rubidium. A solid product again results. Finally, cesium melts quickly, then reacts, also producing a solid product.
As with the family of noble gases and the family of reactive nonmetals, these metallic elements also show marked similarities. Perhaps they are also a chemical family. All these metallic elements are stored under oil, since they react with both air and water. Let's check the reactions with water. Here's lithium. Hydrogen is produced. It dries the lithium around the surface. Next is sodium. The sodium reacts similarly. Potassium reacts with such vigor that the hydrogen produced bursts into flame. Rubidium is similar. Cesium reacts almost instantaneously. Their similar properties show that we have isolated a third family of chemical elements, called the alkali metals.
This 3-column table can be expanded by further experiments of the type we have seen to produce a periodic table of the elements. Each column contains a family of elements. The number of electrons per neutral atom increases regularly in each row and from one row to the next. Each of the elements is different from all of the others, but all members of a family have some similar properties. While the noble gases are all relatively inert, they do form a few highly reactive compounds. In the early 1960s, chemists tried mixing xenon and fluorine in equipment such as this. The mixture of xenon and fluorine passes through a nickel tube heated to 400 degrees Celsius. A white solid product collects in this cold trap. Analysis shows the solid to be a pure compound, xenon tetrafluoride, XeF4. Xenon tetrafluoride is extremely reactive. For example, it reacts vigorously with water. Krypton compounds are even more reactive, emphasizing the fact that the noble gases do not form stable compounds.
A quick review. We first saw samples of most of the chemical elements, then we studied the reactivity of all the gases. 5 gases reacted with none of the other elements used. They are called the noble gas family of chemical elements. Atoms with the number of electrons represented by these atomic numbers are especially stable both as noble gases and in compounds. We studied the nonmetals having 1 less electron per atom. These halogens, in many of their reactions, gain 1 electron per atom and achieve the noble gas electron number.
We also discovered a third chemical family. Each atom of these alkali metals has 1 more electron than a noble gas. Each atom tends to lose its last electron to reach a noble gas electron structure. Thus, the noble gases and atomic numbers are keys to classifying the elements into chemical families.